So first of all, I'd like to thank the organizers for the invitation. It's a very beautiful place and a very interesting conference. And I should begin with an old anecdote about a concert that took place in Paris in the 1930s when a student of Enescu, the great Armenian composer, he was also outstanding violinist and violin teacher. So his student was giving a concert. And the student was playing the violin, and Enescu was playing the piano, accompanying him. And Alfred Cortot, the great French pianist, was turning the pages. And then there was a review next day, supposedly, in the newspaper that said that the person who was supposed to be turning the pages was playing the violin. The person who was supposed to be playing the violin was playing the piano. And the person who was turning the pages was supposed to be playing the piano. So the person who was supposed to give the 5 p.m. talk got on the organizing committee. So the person who was supposed to give this talk had to give his talk. And I'm the one who's filling up. So to begin, let me write down the problem. So I'm going to be talking about the Schrödinger equation. So V of x is a mean zero random potential, and we'll assume that it's as smooth as you want. We don't care whether it's, so it's not a Stratonovich, it's not eta, it's just a very smooth random potential with a correlation function that will mean zero, and the correlation function I'll denote by r of pi. And the way I would like to think about this problem is that epsilon is a parameter to be given by a medium. So kind of from applied math point of view, you have a given medium which has weak fluctuation, so epsilon is much less than 1. And then you can probe this medium in any way you want. You can send there signals which you can suit to whatever goal that you want to achieve, and you can take measurements wherever you want, meaning that you can take measurements at any distance in terms of epsilon away from the source. You can take sources, send sources which are macroscopic, microscopic, and you can wait as long time as you want. But epsilon here, one thing which you are not allowed to do is you're not allowed to change epsilon. So epsilon is a fixed small parameter. Of course, everything can be retold in the other language, but that's a convenient kind of point of view for me. And what we are interested in is for given, let's say, initial data, what is the first time T epsilon when something happens? Which is the most common question asked probably this week. So what will T epsilon depend on? Well, first of all, of course, it will depend on the statistics of V, it will depend on the initial data, it will depend on what you want to measure, and so on. But typically, what one should expect, because the randomness is of size epsilon, and if everything is canonical, this is the most natural candidate from a central limit theorem. And one question is, when is it true? Or rather, it's clear that it will be often true. So rather, the more interesting part is, when is it not true? Now, what you want me to define happening? Yeah. Okay, that's a very good question. I should have told you that. I can take the road of David and not say what it is. But basically, you look at the evolution with V equal to 0 and V not equal to 0. and you look at some object. And depending on the object you look at, it can diverge from the homogeneous evolution at a certain time. But it can be that the time at which it diverges from the homogeneous evolution depends on the object. And then, so something will happen. So for example, if you look at the light coming into this room, if you want to look at when the light leads this side or that side, it happens at different times. So if your observable is this side of the room, it's one time. If your observable is this side, it's a different time. So what happening depends on what you look at. And the typical way physicists have been looking at it is the radiative transport model. And that supposedly goes back to Rayleigh. I couldn't find the original paper by Rayleigh that would do anything of this sort. But I assume it exists. And then, of course, there was Chandrasekhar in the 30s, 40s, and so on. So the model is very simple. You forget about anything about the microscopic dynamics, and you declare that you have an energy density in the phase space. So x here is the position, xc is the momentum, and you write down a balance equation. So this is a scatter. This is just streaming, reflecting the fact that xc is the momentum. This term is some kind of scattering cross-section, which you either put down empirically or try to derive from the microscopic model. And then this is scattering in from other directions, p into direction xc, and this is scattering out of the direction xc into direction p. So all the time waves encounter scattering, something scatter into direction xc, something scatter out of the direction xc, and this is the energy balance. And this is called the radiative transport equation. And the problem of the derivation of this from microscopic models, there are very few. So there are very few rigorous derivations. So this model is extremely universal, in the sense that people use it in all kinds of applications, for acoustic waves, for elastic waves, for medicine, for God knows what. But there are very few rigorous mathematical proofs that this kinetic limit holds starting from some microscopic equation, microscopic wave equation. But for weakly random Schrödinger equation, there are results. So the first one is due to Herbert Spohn in 1977, who did it exactly in this setting, that you start with the Schrödinger equation, and you define what's known as the Wigner transform. And I'm not going to talk too much about Wigner transforms. I will just write down what it is, but I don't want to go into details of its properties. And then what Spohn proved was that the expected value of Wigner transform for the solutions depend on epsilon, because solution depends on epsilon, converges to the solution of the radiative transport equations for some times less than. So there exists T0, which depends on the power spectrum or the correlation function of the random potential, such that this is true. Let me put a bar here so that statement would make sense. So that was Spohn in 1977. And the annoying feature of this, the question?
The two W's are the same.
This W is, now this W, they are the same, but this was introduced without any connection to any microscopic quantities. So this W, you just say, there is some wave being scattered around. Let us call the energy at the position x going in with momentum xc, W of txc. Then you just write down this balance equation the same way you write continuum mechanics equation. You say energy has to be conserved, so that's the way it is conserved. So this is completely no connection to microscopic dynamics. What Spohn did was he defined this object where psi is the solution of the Schrödinger equation, and he proved that this result. Yeah, but yes. Epsilon is up there. W epsilon. If you want to be pedantic, but huh? This is what the question.
So the two W's actually turn out to be the same, or it's only the fact that they both converge?
So this W is not defined, right? So this W you just say, let it be. So really this W is that W, right? The solution of the equation. And then you show that for the solution of the Schrödinger equation, after a long time, in large space rescale, and you get this. Huh? So sigma, I was planning to put it up, so it's okay, is where r hat is the Fourier transform. Wait, I put the correlation function someplace there. So r hat of xi is the Fourier transform of r of x. So this is the power spectrum of the random potential. And yeah, of course. And the assumption that is made, so Erdős and Yau proved it for all T0. So convergence here is for all T0, it converges uniformly in finite time intervals. And that was done in about 0.9, 0.1, or 2 or 3, something like this. And the big restriction here is that V is Gaussian. Because all the proofs are very proletarian. They don't, so one of the purposes of this talk is to show you that, I'm not going to go into the details of the proof, that there is an interesting problem which requires an intelligent approach. So the proofs which go here, I will talk a little bit more about them. They're very brute force, and you don't learn anything from them. In fact, apart from the fact you know how to sum diagrams. That's the only lesson from the proofs, not much more. So this is what's known. And going back to Stephane's question of what is the scattering cross-section, there is an important conserved quantity here, which is 1/2 integral of mod grad psi square plus epsilon now as epsilon goes to 0, you of course get the energy which is conserved. And this delta function of xi square minus p square, the energy here is related to the limit as integral of mod xi square w of t x xi dxi. And preservation of energy implies that momentum should be conserved in scattering. So the scattering has to be a delta function of xi square minus p square. And that will be quite important. And there are also much simpler results that we did for the time-dependent potentials. I'll talk about them at the end if I have time. But for now, let's stick to the time-independent potential, which is a little more complicated. And so this is what was done by Spohn and Erdős and Yau. And then a couple of years ago, Guillaume and his student Nin Yao Zhang, I think it appeared in 14 or 15, but it was really done a couple of years ago. They looked at the following problem. They asked an illegal question. And the paper is called Homogenization with a large random potential. Homogenization of Schrödinger So the question that Guillaume asks was the following. Suppose I have a Schrödinger equation with mean zero initial random potential, which has strength 1. Well, if it is mean 0 and you wait time of order 1, then the dynamics of this will be exactly as the dynamics of a homogeneous Schrödinger. This thing will average out. Then, because you wait only for time 1, there you wait for time 1 over epsilon square, as either Stefano or Tomasz pointed out. But here you wait just time 1. Then you start to increase the strength of the potential. And the question is, if I want the effect to be non-trivial by time 1, what should M be? This question is illegal from the point of view of what I talked about here, because here you play with the medium. It's not that you fix the medium and you probe it. You ask, you're going to change my medium and see what kind of potential will produce an effect of order 1. So that's an illegal question. But nevertheless, you can ask illegal questions. And what they proved was that if M is equal to 1, then psi of t and x converges to psi bar, which is the solution of the homogenized problem. Let's put VF. Bar is not complex conjugate, it's just that. And of course, psi bar 0x is psi 0 of x. And they've shown that they got a formula for the effective potential, which is integral of r hat of p over mod p square dp. Huh? There is a constant. But I mean, this constant? Yeah, it is a constant. Yeah. But it has to be a constant, because there's no x dependence here, so it has to be everywhere the same if this one is statistically homogeneous. So it has to be a constant potential. So it's just a constant phase shift. And there's an interesting historical curio. I was recently preparing some other talk, and I looked back at the original papers by Rayleigh. And Rayleigh, there was a paper from, I think, 1871, in which he writes, I'm almost literally quote, that if you consider a medium where a wave is propagating, which is much longer than the size of the small scatterers, then then it's well known that the amplitude of the wave will not be affected, but the phase will be affected. And here, this is exactly what you have. Because the potential is real, then this just modifies the phase of the wave by a constant factor. So this is something that Rayleigh somehow knew many years ago, and he quite precisely specified the homogenization regime very carefully. The correlation length of the distance and the correlation length of the random scatterers is much larger, is much smaller than the distal wavelength and so on. No, without any time rescaling, because you put the large thing.
No, but
from psi to psi bar, there is no time rescaling. Because it's a very strong potential, right? It's 1 over epsilon, Vfx over epsilon. Huh? Of course.
But this constant can be infinity, so you need a condition on R.
A very good question. But I'll ask this question in a minute. It is exactly this question that we want to ask. Okay, now to turn it into a legal question, you do the following. So that's equivalent and so the Jada would have the long time rescaling, to the following problem. You look at I phi t plus Laplace phi minus epsilon v of x t is equal to 0, phi of 0x is equal to phi 0 of psi 0 of epsilon x. It's exactly the same problem. So phi of psi of t and x is phi of t over epsilon square x over epsilon. So therefore, what Guillaume and Zhang did was not homogenization of Schrödinger equation, but the large random potential. It's a weak random potential, but initial data is very, very slowly. And you choose epsilon here for a purely bureaucratic reason. Because as you'll see later, if you choose something else here, you are not going to get this nice Laplacian here. Right? Because if you have wavelength 1 over epsilon, and you go for time 1 over epsilon squared, the effect of Laplacian will be exactly 1, like in all parabolic scalings. So this is what they prove. And the fact that the effective potential is real, so this is a convergence in probability. So this is homogenization, right? Limit is not random. And if the limit is not random, effective potential has to be real, because energy, total energy is conserved. So if the total energy is conserved, then, if you have a non-real potential, then energy would either grow or decrease. And since it neither grows, since it's conserved, the only possibility is that the effective potential is real. And the next question that there are two questions that you can ask trying to connect these problems. Not try to use the fancy technology. Hopefully. So what we would like to do is two things. First, we'd like to address your question, or at the second, we'd like to address your question. But for that, first, we need to connect these two problems. So let us connect. How do you connect? And you'll see in a minute why it's interesting to connect, again, because of your question. So if I look at the Schrödinger equation with initial data which has some parameter kappa, then kinetic regime and you can see that the kinetic regime, there is no homogenization. Corresponds to kappa equal to 1. And we know that homogenization of Bao and Zhang corresponds to kappa equal to epsilon. Now, taking kappa equal to epsilon is really very, in Russian, it was saying voluntaristic. It's very arbitrary. Well, why this epsilon, which you take with the initial data, has nothing to do with that epsilon, which is the strength of the random potential. It is a very distinguished limit, right? So why would you probe your medium with something which is exactly coming for the strength of the potential? There is no reason to tie these two parameters. And then the question is, so what happens for other kappa? And there are two possible behaviors. Either, so there is an argument in favor of, so basically you can look at kappa, let's say, between epsilon and 1. Let's say kappa is epsilon power 1 over 100. And you can ask yourself, am I going to get some kind of radiative transport behavior with a very long initial data? Or am I going to get a homogenization with very short initial data, very small scale initial data? So will this homogenize? or will this be random? And in principle, if you look at the physics kind of literature point of view, it's well known that the field is very, very random. It's the reason why people introduced the Radiative transform is exactly to avoid dealing with the wave field, because the wave field is highly oscillatory and totally random. You can never deduce any information in real experimental measurements out of the wave field, but you always take some kind of correlations. You never deal with, in practice, in data, with the field, because it's very random. And that's the argument that somehow this is a pathology, because, okay, you can prove here homogenization, but in general, you never observe this kind of thing. On the other hand, if you take a purely bureaucratical and mathematical point of view, well, I took here kappa equal to epsilon. But what I'm doing, I'm taking macroscopic initial data, which varies much slower than the potential. Why should be there any special about kappa taking exactly epsilon? You may think that if I take any macroscopic data, as long as it's macroscopic, you would have homogenization. But then you would have to explain yourself to physicists why don't they see homogenization, but only see kind of random patterns. And the second question is exactly what I wonder if I will ever be able to get it back. Okay, let me try to do sophisticated one. I know there are buttons. Okay. The second question is comes from the following observation. If you look at the, as you wisely suggested, the V effective is integral of r hat of p over mod p square. And let us assume that our potential, so all theorems that I so far mentioned, I didn't state them precisely, but they all assume roughly that the correlation function is in the Schwarz class. It decays very rapidly. It's not exactly Schwarz class. For example, Erdős and Yau assume that it's Sobolev space 20D, 20D. So you have to have 20D derivatives and all have to live the LP 20D. But it's as good as Schwarz class. So they all assume that you have extremely nice correlation functions. But if you forget about theorems and you just say, let's take a correlation function which decays like 1 over x to the power r with some power algebraically, then this is finite if r is bigger than 2. It's a computation. If you take the total scattering cross-section and transport, sigma of k, which Stefano asked me to write down, it's less than infinity when r, it's finite, is bigger than 1. So there is a range of potentials where there are potentials where the effective potential is infinite, but the total scattering cross-section is finite. And that's what we would like to investigate. The situations where when this guy becomes infinite while this one may be still finite.
Sorry, I have another question.
Yeah.
What is the space dimension?
I will specify. So for the theorems, it's, let's say d greater or equal than 3. Okay, in one dimension it's obviously false.
Because I have problem with convergence of the origin.
Of course, its dimension is greater or equal than. Erdős and Yau have the dimension 2, Sponner has the dimension 3 and higher, but let's say dimension greater or equal to 3. So this is, and the ball, of course, is also greater or equal to 3. Now, how are all these things proved? They're proved all in the same way. You start with the Schrödinger equation. You go to the Fourier transform. So you Fourier transform the most multiplic square. This becomes a convolution. It becomes an ODE, right? You write it. This is, if you look at this as a force, you write it. You iterate. You get an expression which will say psi is equal to psi0 e to I, psi0 hat of t. So psi of t hat psi is equal to psi0 hat of t xi e to I mod psi squared t over epsilon. squared plus there's the integral, which is rho v hat of p. Then we have psi hat here, and then there is some phase here. And then you iterate this. And the difference between Spohn and Erdős-Jau is that Spohn iterates infinitely many times, and because of that he has a finite time. And Erdős and Jau cut at finite n, which depends on epsilon, and then they do some clever resummation so that everything becomes. So when you iterate this, so to get the kinetic limit, you take two of these series, you square, and then you take the expected value. And you get many terms like v, 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 and you take the expected value. And since you assume that v is Gaussian, expected value of a product of n, 2n of them splits into sums over products of 2, and you do summation of all diagrams and so on. And then when you do it, it's very hard to improve anything. At least we weren't able to. We tried for a long time to improve and to play with this, and it was going nowhere until one day we were on Skype, and one of us said desperately, how nice it would have been if the correlation function itself would be a Gaussian. And the other said, you're an idiot. But next day, the other came up with a general theory for potentials. So there are, if you take potentials of the following form. So it's a linear combination of Gaussians. You take e to minus lambda square mod p square over 2, some function s of lambda, d lambda over lambda to the power 1 plus r minus d, where s of lambda is some bounded function, positive. So these are all positive. These are all linear combinations of Gaussians. And r of x decays like 1 over x to the power r. In infinite dimension, actually, these are the only ones that exist. In finite dimension, it's not true. But they're very convenient to work with. Again, for a bureaucratic reason. That when you do this iteration, well, what do you have here? You started with xi square, right? So you'll have lots of squares. Xi square, p square, and so on. There are xi squares, there are p squares, and p minus p1, pn squared, so on. But they're all squares. And the correlation function, and they will be product of many correlation functions. And this is also Gaussian. So you have p square here, and you have many, many p squares there. You can integrate this out explicitly, because you know how to integrate out complex Gaussians. After you do that, suddenly the hard problem of estimating oscillatory phase, the whole play of Spohn and Erdős and Jau is playing with oscillatory phase here. Instead, what you get is linear algebra. You get some kind of determinants of the quadratic forms that appear here. They have some explicit form, and you can deal with that. So that's basically, as soon as you take potentials of that form, instead of dealing with complicated oscillatory phase integrals, you deal with linear algebra, which is also kind of tough for us, but it's infinitely easier for us than dealing with the oscillatory integrals. So that's the class of potentials which we are going to consider. And an object that you would like to take is the following. If you go back to Guillaume's result, up there. I don't know which one is which. So in Guillaume's case, they take time t over epsilon square, and there is epsilon x here. And the total phase that you gain, the wave number here is epsilon square, and you get 1 over epsilon square from the time. This is 1. If I put kappa as here, then I'm going to gain, and kappa is less than epsilon, I'm going to gain a large phase. So if I'm going to look at the solution of this problem itself, that would be rather stupid because of the huge phase you're going to accumulate here unless kappa is equal to epsilon. So you have to compensate for that. And the object that accounts for that is a compensated wave function which is defined as zeta, xi, and xi. I hope you can distinguish which one is zeta, which one is xi. E to I t mod xi square over 2. Sorry. Xi hat t and xi. So this one takes out the rapid phase. And now let me give you some. So basically, what this does, from the philosophical point of view, you have think of Schrödinger as a fast underlying dynamics. And the random potential is a slow dynamics. So what this does is factors out the fast underlying dynamics. Because the phase will rotate like crazy. You'll take it out, and you only will track the combined effect of this fast dynamics with the slow dynamics, which comes from the random potential. And then the result is the following. So you take the microscopic case first. So the order 1 kind of level of difficulty is to redo what Erdős-Jau and Spohn did under weaker assumptions on just that this is finite. So let's, so this is the result. And that's joined with Chen, with Thomas Chen. You can imagine the number of puns you can make when you work with Thomas and Tomasz. And that's, I don't know. So the result is the following, that suppose that effective potential is finite. So this is our hat of p rho mod p square. And d is greater or equal than 4. Hopefully tomorrow by the evening it will be 3, but let's now say 4. Then we have 2 results. First of all, expected value of zeta epsilon of t over epsilon square xi converges to e to minus some diffusion coefficient times t C0 hat of xi. And second, the expected value of zeta epsilon squared of t, again time is t over epsilon square, converges to solution of the kinetic equation minus the ballistic part. So in the kinetic equation, there is a ballistic part which encounters no scattering that you have to subtract. So this basically the Erdős-Jau result for this kind of potentials was but Spohn-like, finite time. Finite macroscopic, right? So it's T0 over epsilon square. So this is one. And for macroscopic data, you assume, so this is microscopic data. Kappa equal to 1 means that, did I say kappa equal to 1? No. That initial data varies exactly on the same scale as the random potential. And as you can see, solution is random because the expected of the second moment is not square of the first. So there is randomness persists. Now, if you assume that kappa is equal to epsilon to some power, where beta is positive, this is macroscopic. That initial data varies slower than the random potential, but not all the way to what Guillaume had, but arbitrarily fast but slow. Then the L2 norm of z epsilon hat of t over epsilon square xi minus e to I vf t over epsilon square vf t times psi0 hat of xi in L2 goes to 0 in probability. So there is homogenization. So no matter how, so any macroscopic data, no matter how little macroscopicity there is, homogenizes. And the homogenized problem is exactly like what Guillaume had here, except you cannot put Laplacian, because if you put Laplacian on high frequency, because it's kappa is not exactly epsilon, this would have a coefficient something like 1 over kappa square. You don't want that. So you take care of that phase by phase compensation over there. But as soon as you compensate the phase, what remains is deterministic. It's totally not what you see in any kind of simulation or experiment. But nevertheless, it's true. I mean, that part I believe in this theorem. So which means that somehow the genericity and the applicability of the transport is really something which should be understood better. And this is, again, as soon as effective potential is finite. So R is bigger than 2. Now, this theorem is not completely, it's not the best you can do. I mean, no, so far it's the best we can do. But it's not the best someone should be able to do, because in reality, this should hold not when effective potential is finite, but when the total scattering cross-section is finite. And there was somewhere on one of these blackboards, this one, there was a comparison that effective potential is finite if the gradation function decays at least 1 over x squared, but the scattering cross-section for the transport is finite if gradation function decays like 1 over x. And what we have is the range when effective potential is finite. But it seems non-trivial to generalize. And then the next question you can ask is what you have asked half an hour ago: what if the effective potential is infinite? And then in this case, we have partial results, which, let me just say with words, because if I'll start writing, I will mess up some numbers, supposedly. Think about it in the following way. Take the initial data, which is 1, which means that kappa is 0, right? You take initial data, which is constant, and let this thing run. Then, if V is random potential with effective potential, which is infinite, then this initial data, which is 1, will be affected on certain time scale, which is shorter than epsilon to minus 2. So then, if psi0 is identically equal to 1, then T epsilon is equal to epsilon to some minus alpha, where alpha is, let me put 2 alpha, and alpha is less than 1, but it's some number which you can compute. And on this time, zeta epsilon will converge to psi0 hat of xi times e to I fractional Brownian motion of certain parameter h. I don't want to write how alpha and h depend on the various things. And what we can prove is that there exists a critical, so now you take kappa equal to epsilon to the power beta. So you go away from kappa equal to 0, you take bigger kappa. They certainly cannot become random before this time. This is the minimal time it can take for anything, any initial data to be affected. But at this time, there exists a beta bar, which is explicit, such that for beta, which is less than beta bar, you have the same result. Huh? Well, there is a diffusion coefficient here which depends on xi. You're completely right. But the amplitude is not affected. On this time, it's only the phase that's affected. What happens to the amplitude is a story that Christoph Gomez will do one day. He did nice things about time-dependent potentials about this. And, but what we don't know at the moment is what happens for beta, which is between 0. 0 means kappa equal to 1, so it's this case. So this is transferred. This is long in macroscopic initial data, very macroscopic, so to speak. And this intermediate range, it looks like for time-dependent potentials you still get homogenization, but it's all conjectures. I don't want to speculate. But the overall idea is that as you slowly go from this decay to that decay, the more and more frequencies will experience this kind of pathological fractional behavior. And eventually, when r is equal to 1, you're going to hit the kinetic regime, and there you're going to destroy this result, and you'll have something else. So there's a whole diagram of various things that can happen in terms of, for each r, which is between 2 and 1, there is, so this is beta equal to 0. This is kinetic limit. So this is some kind of fractional Brownian motion behavior. And here, that's proved. Here we don't know how this moves here. What happens when r is less than 1? That's also completely open. And I think that this cute little trick, I don't know, cute, it's not cute, but with this trick of taking Gaussian correlation functions actually makes it feasible that one can go much further than without this form. And I'll stop here.
That's it. What you know without taking the mean in the result?
In which of them all?
For example, okay, even up there, okay, or in your statements.
So let me do the following. In the kinetic limit, in the situation when the data is microscopic, right? Kappa equal to 1 means that you have just initial data which is the same scale as the potential. Then when what is known for time-independent potentials is exactly that. You have the expected value converges to the for time-dependent potentials, you can show that actually the compensated wave function converges to the mean plus a Gaussian, and the Gaussian has this variance. We don't know we didn't look at the correlation between the two, but that's only for time dependent. I'm sure that here you can get the similar result, but it's many more pages.
But I mean, it depends on psi also. So I mean, you fix psi.
So you fix psi, okay, and then pointwise in psi.
But you don't know the
random. But we don't know
field.
the law in the no. Okay. And for the homogenization, there is nothing to ask because it's homogenization. So you converge in probability. And but in this case, in the pathology, in this, there are also things.
Other questions?
One question will be, without just fixing epsilon or rescaling diffusively space-time, there is any progress towards convergence
for strong potentials?
To heat equation?
For strong potentials.
There
is no epsilon, yeah? In the
with the noise potential.
Here.
Yes.
No,
But it's expected to be true in dimension 3.
probably.
Okay.
Well, there has to be sufficiently high energy, at high energies. You have to do something about localization, right? In dimension 3, and even in dimension 3, with high energy, you have localization. You have to deal with that.
Mm-hmm.
So if you have sufficiently high energy, you're not going to be localized. But to prove transport,
Because somehow all these limits, you get this kinetic equation. This kinetic equation can be again rescaled and obtain heat equation
Of course,
from this.
of course,
So,
yeah.
so it's a kind of two-step.
but
If you want to go,
yeah, but I think the honest answer is nothing is known.
not you know. That's
I think it's a hard problem.
Okay, no other questions? Let's thank the speaker again.